All right, so it's asking us now. Um, this is an organic chemistry question, so we're looking at number 3 here. It's asking, provide the major organic product for each of the following transformations. So we basically have one guy here, and we have a cyclohexanone here. So we have a ketone group, and this here is now we're jumping into organic chemistry here, right? So this here is much again, we have client questions from all over the place here, but we have here we have a cyclohexanone here first. So let's look at let's go clockwise, and maybe for the sake of time, what we can do is we can actually just look at the answer and see and kind of reverse engineer the mechanism here, just so for the sake of time, so that we can kind of move on to the other questions, because there's technically 6 questions here in the in one question here. So the first question, or maybe I'll do one for you here. So the first one here is the first product here. If I'm looking on this left-hand side here, I'm going clockwise. I'm reacting cyclohexanone with lithium aluminum hydride, and I'm working it up with acid work up here. So we know that for a fact that lithium aluminum hydride here is is oxidation. It's an oxidizing reagent. Sorry. That's what I'm trying to say. Oxidizing reagent here. So what we can do is we know that if it's an oxidation reaction here, what we can do is we're looking at the carbonyl group, and we're seeing that lithium aluminum hydride is a reducing agent, not oxidizing. I'm mixing it up with potassium permanganate. Sorry. So we know that LAH is a lithium aluminum hydride is a reducing agent. So what we can do with our first guy here, LAH, I'm just going to use LAH as my shorthand and acid work up here. We know it's going to be a reducing agent. So I'm going to reduce this ketone back into a alcohol, right? We can reduce this to an alcohol here. So we know that for a fact that number 1 here is a cyclohexane, and then it's actually a cyclohexanol, right? And we're reducing this carbonyl group back into an alcohol. So this is our answer for number 3 here. And as you can see, they got it here as well. They reduced the ketone into an alcohol here. So number 1 here is correct. Let me look at number 2 here. So it's reacting with some sort of benzene group, benzene amine group, here, and then again with a little acid workup. And this here is going to make this here would be kind of a nucleophilic substitution, right? So you have again the benzene group, or not the benzene group, sorry, the ketone group like so. We're reacting with this benzene with NH2. And then an acid workup. So you can think of this as, again, you can think of these guys here as partial negative. This here is partial positive. And then this here would be, again, these lone pairs are partial negative. It's going to be attracted to this carbonyl. It's going to bump this guy up out here. So you get some sort of intermediate, like so. You would get, and this would have a negative charge here. Yeah, and here you get the benzene group like so. You get some sort of negative charge. Oh, this is not partial negative. Sorry, this is actually contains a negative charge here. And then what it's going to do again, the H plus it's going to create some, it's going to protonate basically OH2 here. So you would get something like this, or protonate this O minus, sorry, not OH2, and it's going to become OH2 minus here. So I'm just kind of skipping steps here, but this is OH2 minus. This will have a positive charge now here, and the lone pairs from the hydrogen will collapse here, and then kick out this OH group to form our final product here, which is the cyclohexane group bonded with the nitrogen, or double bonded with the nitrogen, sorry, and then bonded to the benzene group here. So this here is our correct answer. Number 2 here is correct. So this is great also. Number 3 here is kind of the same mechanism as our benzene group here. Basically, again, another nucleophilic substitution. This N group here is going to attack the positively charged dipole carbon here, and then it's going to shift up, right? So again, you would have the same kind of intermediate like so with the O minus, and then it's going to again protonate using acid workup using the acid to get OH2, and then N here is going to simply kick out this OH2 and eliminate it by creating a double bond here. So this solution is also correct. Very, very similar to the mechanism for number 2. Number 3 here we have this is a phosphorus kind of we have a phosphorus ion and also a phosphorus cation, and we have this is a methyl anion complex. What it's going to do, indeed, it's going to reduce this O minus into an alkene. So it's actually a very, very strong reducing agent, and it can actually reduce it all the way back to an alkene because of this because of this kind of negatively charged methyl group is very, very, very strong as and it's just being stabilized by this positive phosphorus group. So again, this solution here is also correct. We have diol here. If we react it with a diol and also with acid here, again, exact same thing is going to happen. The negatively charged oxygen here is going to attack the positively charged carbon here, and then this guy here will make an it'll make a cyclic group as well, because we have the O minus is going to attack this side, and then the other O minuses can also attack this side as well. So you would create a cyclic group using a diol here, and then finally what we have here is, I don't think they drew it well here, so let me redraw this one for you. But you're going to react it with basically cyanide. So you have a ketone here. I'm reacting with HCN. What you're going to get here is you're going to, again, we know that this here is positively charged. So this is negative. This here is positive, and you know that again, this nitrogen here is very negative, right? This here, the lone pairs here, going to attack this guy, bump this up. So you're going to get something like this. You're going to simple SN2 reaction here, and this will be CN here. So this here is going to be our product for the last question here. So this is just simply SN2 substitution, and you're going to get a CN group, a cyanide group on your cyclohexane. So this solution here is correct. They don't really have analysis, but I'm just saying it's the correct solution. They didn't really draw up the mechanisms like I did, but totally fine as well.